Hello and welcome to part 2 of our video in chapter 11. So the previous video I did was a little too long, so we're going to redo this part here and go over it real quick. Alright, so for part C, you construct a 95% confidence interval from the previous problem here. With our previous problem, we have calculated our x bar delta, and we already have our standard error of x. So we know our x bar delta is 4.8333 plus or minus. We don't know what our t of n minus 1 degrees of freedom of our cumulative probability of 1 minus alpha over 2. We do know we're going to multiply it by the standard of x, which is 0.3073. We know our t of 6 minus 1, which is going to be 5, times the cumulative probability of 1 minus alpha, alpha being 0.05, over 2, is going to be 0.975. So we're looking for our T5, cumulative probability of 0.975. So we go to the back of the book, find our t statistic that matches that. When you do that, you'll get a value of 2.571. Multiply 2.571 times 0.3073, which is our standard error of x. You get a value of 0.7901 plus or minus our 4.8333. And we're going to get our confidence interval to equal 4.0432 to 5.6223. Don't have a whole lot of room to write here, but this is where we would state that we are 95% confident that the true mean is between this interval. So that is 7C. So we move on to 8. Suppose a researcher is interested in the relationship between the average hours of sleep per night and the number of health outcomes. Suppose the following table represents a simple random sample. A simple random sample suitable for a normal approximation from participants in the study. So part A is asking us to construct a 95% confidence interval for the average hours of sleep. Provide the correct interpretation of the interval. So we need to construct a confidence interval. Once again, our confidence interval is x bar plus or minus t of n minus 1, comma, 1 minus alpha over 2 times the standard error of x. So in order to calculate the standard error of x, we first need to know the standard deviation. So in order to calculate standard deviation, we're going to add all these up and divide by the total number here, which is n is going to equal 6. And we're going to find that our average is 6.4. It's going to equal our x bar. And we're also going to find our standard deviation when you work all this out. So you have x bar, so you take 6.4 minus 6.4 equals 0. Then you're going to square that value, add up the sum of squares. Remember our standard deviation formula. And then when you do all that work, you're going to get a standard deviation equals 1.5505. And now we have all the information we need to do our confidence interval. So our x bar, like we said, is 6.4. We're going to plus or minus our t of n, which is 6 minus 1. And then we're going to find at 95% confident, that's alpha equals 0.05. So 1 minus 0.05 over 2. So we're trying to find our degrees of freedom of 5 at 0.975. Well, luckily this was already calculated previously up top here, so we can take the same value and use it again. So that's going to equal 2.571. Our standard of x is going to be the standard deviation, which is 1.5505 over the square root of n, which is 6. So our standard error of x is going to equal 0.6328. Put this all together in our formula. 6.4 plus or minus 2.571 times 0.63298. I like to go super slow, so it's 6.4. Multiply this out. You're going to get 1.6274. Confidence interval is going to be 4.7726 to 8.0274. Prior to correct interpretation, our interpretation is going to state we are 95% confident that the true mean, which is hours of sleep here per night, lies within the confidence interval of 4.7726 to 8.0274. And that's how we do part 8. Moving on to question 9. An investigator wants to test the effectiveness of a new weight loss medication at reducing BMI. In order for the medication to have a high chance of receiving a sizable investment, the mean difference in BMI must be greater than or equal to 5 kilograms per meter squared in a pre-post test of BMI in participating individuals. Suppose the following table represents the results from a simple random sample of individuals enrolled in a study. Assume a normal approximation is acceptable. So here we have a study where we literally have pre, post, so we know we're going to be measuring the delta between both of these. And we also know that our mean difference, right? So we even said mean difference in BI must be greater than or equal to 5 kilograms per meter squared. So they want to increase it by that much. So part A, is there sufficient evidence provided by the SRS to conclude that the medication is successful at reducing overall BMI in the population by more than 5 kilograms per meter squared? Use alpha 0.05. So we should write our null and alternative hypothesis because that will make things easier to see. So our null hypothesis is going to be our mu delta is equal to 5, and our alternative hypothesis is going to be mu delta is going to be greater than or equal to 5. Sometimes you don't see greater than, so we're just going to be greater than or equal to 5. But in reality, now I think about it, it can't be greater than or equal to, because if it's equal to 5, then you're going to be, well, your null hypothesis is going to be, you're going to fail to reject it. Anyway, moving on. Alternative hypothesis, well, it can be both. That'll be fine. Moving on, so now we need to figure out our t-statistic. So our t-stat for our paired t-test is going to equal our x bar delta minus mu delta all over standard error of x. And in order to find our standard error of x, we have to get a standard deviation from our delta population. So once again, you take your pre and post test, so you can take 32.5, subtract it from 24.5 and get 8, and then this is going to be 8.5 and 11.2, 8, 8.5, add them all up, and you're going to get a value of 44.2, which is your sum of delta, and then your x bar of delta is going to equal 8.84, and your standard deviation when you work all out of delta is going to equal 1.3428. Having all this information, you're then going to be able to plug in the values to get your t-stat. T-stat here is going to be 8.84 minus our mu delta of 5 over our standard error of x, which is 1.3428, divided by the square root of n being 5 here. work this out. It's going to be 3.84 divided by 0.6005. So it's going to give you a t-stat of 6.3947. When you go in the back of the book and try to find at degrees of freedom 5, or degrees of freedom 4, n minus 1 is 4, so degrees of freedom 4, and you're looking for a value of 6.3947, you'll see that that is, as you get in degrees of freedom 4, between, an upper tail probability, 0.0025, 0.001 is where that 6.394 is going to fall. So it's going to fall somewhere in between there. We don't know exactly where because we don't have an actual calculator telling us, but we know it's going to fall somewhere in between there. The true p-value, if you're curious, the true p-value is going to equal 0.0015, which is in between this value here, and what we would state is that the p-value is greater than 0.0025 but less than 0.001. Either way, at an alpha 0.05, we're going to reject the null hypothesis because our p-value is going to be less than our alpha, and then now we reject the null. We're going to construct a 95% confidence interval and provide an interpretation for it, and does this interval further support your decision in the hypothesis tested above. So when we construct our confidence interval, just like we were doing before, it's our x bar delta plus or minus t of n minus 1, comma, cumulative probability of 1 minus alpha over 2 times the standard error of x. We have most of these values. Our t of 5 minus 1, so it's going to be our t of 4, comma, 0.975. It's going to give you a value of 2.776. So we're going to have 8.84 plus minus 2.776 times the standard error of x, which we already calculated from above, 0.6005, 8.84 plus or minus 1.667. It's going to give you a confidence interval of 71.173 to 10.5070. And that is our confidence interval for our pre and post test of this new weight loss medication. So the true value of the mean should fall somewhere in between here. Okay, and that's all the time we have for this video due to YouTube time limits. So I will catch you all on